All right, good morning, everyone. So a couple of things before we officially get started. So we have a lecture scheduled for next Tuesday, which is at the same time as the Asamblea. So I don't know if that is going to interfere with anyone's plan to attend the Asamblea. I could try to reschedule it, but I would have to speak to the speaker. So my plan was to just go ahead and then we'll see based on people's schedule. The second thing was about the discussion with the groups regarding the actual annotated bibliography. So I've heard back from some of you. Looks like next week will be best for everyone. So we just have to identify a time frame. I'll send out another email to try to find out a time frame that would work for everyone. I don't know if people have things after class on Tuesday, because that could be another thing that we could do. But that obviously would require us to be in person for the virtual thing, and then that would interfere with the Asamblea. So I think Wednesday would be better. Okay. All right. So what we're going to do is continue our discussion prior to what Maria Contel, who was our guest speaker last time. So we were entering into looking at the role that metals play with regards to infection. And early in the course, we discussed a bit about this concept of how the immune system has a natural response to pathogenic things, where in the case of iron, as I mentioned previously, it has a way of suppressing the iron that's bioavailable for pathogenic species. And then for other metals, it depends on whether they are more toxic in nature. The body has molecular mechanisms for trying to control the amounts that are present in the body. So what we're going to look at today is applications where metals are being designed in compound form for treatment of invasive agents. So these are just going to be microbes in this context. So just to review a few things that we discussed 2 lectures ago, just to freshen ourselves. So we looked at this idea of the 2 lines of immune defense. And so the idea of having an innate system and having a system that adapts to the presence of pathogenic species. And then we explored this idea of how heavy metals, particularly softer metals like mercury and gold, have this capacity of inducing an autoimmunity. And part of that has to do with their soft nature and how they can interact with soft groups present in biomolecules to make them appear foreign. And that's the source of an immune condition. And then we looked at, in a sense, we revisited gold compounds, because when we first looked at gold compounds, we talked about them in the anti-cancer perspective. That's what Dr. Contel discussed, this idea of gold in combination with other metals to try to explore that synergistic interaction between different metals and exploiting their chemistry. But in the context of gold, in the treatment of rheumatoid arthritis, is this idea of what does gold do to be able to facilitate this type of response? And so we also discussed this idea of gold over time, because it does take quite a bit of longevity in order to actually exhibit an effect, how it itself can induce a type of autoimmunity. And so that's one of the reasons why, one of the major reasons why it no longer is actually prescribed for treatment of rheumatoid arthritis. But what we're going to look at today is this idea of metals playing a role in therapeutics against pathogenic agents. And so we're going to look at metals being engineered to work in synergism with known therapeutic antimicrobial agents, so known antibiotics, for instance, and then exploring this current trend towards looking at unexplored libraries of metal complexes to try to identify potential antimicrobial libraries. And so we're going to look at a recent study that has talks about this idea of trying to reach out to the academic community to see what people have in order to explore their potential for antibiotics. So this would be more in the line of a empirical search, but still it's very interesting what's available for people to try to contribute to this field. And I'll show a little about how some of the work in my lab has also tried to contribute. All right, so where we're going to start today is this idea of exploring parasitic infections in humans. And so here's just a cartoon perspective of just some of the effects or the symptoms of having a parasitic infection. And so it turns out that these type of diseases represent major world health problem, as there are very limited therapeutic options. Some of these are considered rare, and so there's not as many things that are available, or at least not much of an economic incentive to try to create drugs. So the most common and dangerous parasitic infections in the world are the trypanosomiasis, malaria, and leishmaniasis, which is a tropical disease. So there are a number of compounds that do exhibit properties that lend themselves as an antiparasitic agent. And so these are chemotherapeutic agents. So chemotherapy is basically the use of a small molecule for potential therapeutic application. And so what we see here are some of the metals that we already looked at, and also some of the coordination chemistry that we already have explored. So you see the use of platinum and some variation of that cisplatin type of, or in this case, a transplant type of coordination. You also have the incorporation of gold in different structures that are comparable to what we already discussed. So there are a number of metal complexes and different types of metal centers that really lend themselves for this application. So again, a lot of what we're going to look at today, and this is going to be just a brief survey of what people have been doing, is more empirical. And what I mean by empirical is that you're just trying to explore the potential behavior of these compounds, not that you have a specific target in mind. Although some of the things that we are going to talk about are very targeted focused. So let's start with malaria. So this is a disease that's transmitted by mosquitoes and is commonly found in sub-Saharan Africa, Asia, and Latin America. So it's caused by the Plasmodium parasitic protozoans. These are single-cell microorganisms. In 2020, the World Health Organization reported that there were about 241 million cases, and of this, 627,000 deaths. And so an alarming statistic is that in Africa, 95% of the malaria cases and 96% of deaths. So there's a large concentration where this is occurring. And 80% of deaths in Africa were children under 5. So most lethal malaria-causing parasite is this Plasmodium falciparum, which is carried by the Anopheles mosquito. And some of the symptoms is just the common ones of parasites: fever, fatigue, vomiting, and headaches. So without treatment, infected blood cells reach the brain, and that causes cerebral malaria, which leads to neurodisability, coma, and then long-term to death. So here what I'm representing to you, and this is what you would normally see in terms of the infection of parasites, is this cycle. And so we're going to talk a bit about what's happening in this visual. And so what we're seeing is the perspective of a mosquito that's infected or a mosquito that's not infected with the parasite. So let's look at it from the perspective of an infected mosquito. So that mosquito would have a bite in a human. And so what it does, it will release the parasite into the human. And so what occurs is a cycle of the life of the actual parasite, where we get the transformation from the sporozoite form of the parasite and that form getting into the liver. So what we see there is that that form of the parasite will enter into the hepatocytes, which are liver cells, and they will replicate. And what they would then form is into the merozoites, another form of in the life cycle of the parasite. Then that form gets into the blood cells. And so then that propagates and that leads to the propagation of the actual disease. But the same figure can be used from the perspective of a mosquito that doesn't have the parasite, but then bites human blood and then gets infected. So you get the mosquito then now picks up the parasite, and in the actual mosquito, it goes through the cycle of now propagating the life cycle of that particular parasite. So we see how this can propagate in itself, where mosquitoes will infect another person, and then other mosquitoes can then pick up the parasite and further the actual infection itself. So this is pretty much a common depiction of the life cycle of different parasites.
So where does it start? It's like,
where does it start? That's an interesting thing. I would imagine that they're just living organisms that are, because they get picked up by something, then they get spread. So they might be living. So that's something that's interesting. Where do they actually live if they're not surviving in this host? So yeah, I'm not 100% sure. But it's in this context, it's blood spread. But yeah, where does it actually? I should look that up.
Similar to what came first, the chicken or the egg.
Right. So yeah, I think this is a situation where probably it's led to some sort of mutation where these things now become dependent on a host, and maybe in the host they become more, more deadly, or and you'll see some of the reasons why that actually is the case. So here we're looking at a depiction of some organic molecules that have been explored for their antimalarial properties. And so these feature at least two of these compounds, the quinine and the chloroquine, You probably heard of hydroxychloroquine during the COVID pandemic. And so what you see is this quinoline structure here that people have explored, and we're going to talk about in a moment how this relates to iron. And you also have artemisinin. That's also another important compound that you're essentially exploiting this reactive oxygen species there to facilitate some of its antimalarial properties. All right, so we're going to focus on chloroquine, as it is the most successful drug that was developed for the treatment of malaria. And so here you have the chemical structure of that compound, just pointing out some of the properties of it, the quinoline part of it, the pKa's. So you typically will find this administered as a drug in the diphosphate form. So this is a salt as it's delivered. So this was first synthesized by the Bayer Company in 1934. It became approved by the FDA in 1949. So in terms of its another property there, you have the single stereoisomer, but as it turns out, both enantiomers have comparable antimalarial activity. So the mixture of them is perfectly fine in terms of activity. All right, so let's look a little bit about the mechanism of action of this particular compound. And so here we're looking at how the parasite will exploit the hemoglobin of the host. So in this case, think about humans, right? So hemoglobin, a major protein in our blood. And so you see that it will internalize that hemoglobin and it will transport it through that transport vesicle. So you have this vesicle that picks up that hemoglobin and it internalizes into this space, which is called the digestive vacuole. So as the name implies, it's basically going to digest the hemoglobin and take advantage of what the actual protein can offer into the parasite. So I'm going to show you this visual and I'll get back to it so we can see what exactly is the chloroquine doing. So the organism will take up large amounts of hemoglobin from red blood cells, as high as 75%. The hemoglobin serves as a source of amino acids for developing into the merosaur. So basically is proteolizing the protein, because now the protein will become broken down to peptides, amino acids that serves as nutrients for the parasite to be able to prolong and to move on to the next phase of its life cycle. So what you're getting is a series of proteases that are doing this, that are breaking down the protein. So these are some of the proteases that are involved. And so now you're breaking that down to its components, but you're going to also expose what? You're going to expose the heme group. And so the heme group, as you know, has an iron center. In the presence of hemoglobin, that iron center is basically controlled in terms of its redox activity. So we're not exploiting the iron there to be able to transition from iron 2 to 3. We want to stay iron 2 to be able to coordinate oxygen and facilitate transport. But removing all these features from the protein, now you have that exposed unit, which is redox active. And so if it's something that's redox active, as we've talked about before, there's actually going to be something that would lead to the potential formation of unregulated reactive oxygen species, or ROS, or unregulated reactive nitrogen species. And so what occurs then is that there is a molecular mechanism that tries to basically neutralize that heme so that that particular group is no longer redox active. So it becomes sequestered into this unreactive polymeric structure called the hemozoin. So that's observable, or at least it's a really characteristic feature where it forms a pigment that you can perceive. So that's what's called the malaria pigment. So what chloroquine is doing, this function is to try to inhibit the formation of the hemozoin. So when we go back to this figure here, that's where we see the chloroquine entering into the digestive vacuole, and what it's doing is that it's trying to break up the formation of the hemozoin. So here we have the hemoglobin is getting proteolized, broken down into peptides, into amino acids. That's what's going to enable the parasite to proliferate. And then you have the heme part that's getting basically transformed into something that is no longer biologically accessible, or at least not redox functional. And so that's what the chloroquine is going to interfere in this process. All right, so let's talk a little bit about this formation of the hemozoin. So here we have now the heme. It's this particular group here, and now it is capable of being redox active. And so here you see change of oxidation state, we get now an iron-3 center. So one of the things that occurs in this process of trying to transform the heme into this structure that's no longer really accessible is you get this event occurring where now you have the iron-3 formation, and you can exploit the presence of these carboxyl groups that are on the actual protoporphyrin 9, and that leads to a dimerization, at least from this perspective. That's the beta hematin that's starting to form. So that's the beginning stages of this transformation into this monomer and then into a sort of more polymeric species. So you're taking advantage of these carboxylic acids. And so you can see this now more extensively what starts to happen. So you get the iron center facilitating coordination and you get these units now growing, but also the additional presence of the carboxylic acid groups now allowing for hydrogen bonds between different units. And so that's now leading from the beta hematin to forming into this more extensive structure, which is referred to as the hemozoid. And so apparently something that enables this to basically catalyze the process is the presence of the erythrocyte lipid membrane. So that's basically the red blood cell that part of it gets broken down and internalized, and that gets used to take advantage of the lipid group to facilitate the formation of this process of basically polymerization. And so this, coupled with the acidic environment of the digestive vacuole, allows for this to propagate. And so this shows more extensively how, by the formation of this type of structure, you have a lot of different interactions that are stabilizing it. So we have the interaction from the pi-pi stacking that is allowing for this stability. You also have the beta hematin component, where there was the coordination of the carboxylate groups to the iron. And then you also have the component of the other carboxylates that's facilitating the hydrogen bonds between these type of units. So you have these different layers of interactions that's really going to stabilize this group. And basically, the bottom line is that you're trying to prevent that iron from becoming accessible and being redox active. So these beta hematin units interact with one another. They form this pi-pi stacking hydrophobic interactions. This leads to the formation of these dark needle crystals that appear producing that malarial pigment in infected blood cells. That's a characteristic.
So, but the main, so if you stop the production of insulin, so that would also help with, because I think the main issue is that it consumes the red blood cells, so that would be suffocating also, like it suffocates you.
Yeah, to an extent. That's exactly what.
Yeah, but is this like able to also transport oxygen?
So at this point, no. Like, so this would basically be inside the actual parasite. So I don't know like what would happen next, or does it basically just stay there? I think it just basically stays there and is no longer accessible, because I think it probably has no way of getting out. So like it stays basically in this part of the actual parasite, and so that makes it no longer functional. Yeah.
Okay.
So this is a study that was done to try to understand the formation, a little bit of the chemistry behind the formation of the actual hemozoid. So this is not so necessarily relevant in terms of more of the biophysical application, but just kind of giving us some insights to what's contributing to the formation of the heme to the hemozoid structures. So the study at the left is basically looking at different solvents when mixed with water. And so they chose solvents that are not miscible. So they don't actually mix in the traditional sense with water. You're just kind of shaking them and seeing how that can affect the formation of the hemozoid. So you can see that the 1-hexanol does lead to that conversion from the monomer into this polymeric structure. And then you see these other co-solvents. When I say co-solvents, it's the mixture with the water, not as effective. The reaction to the right, what we're exploring here is now we're focusing on a mixture of the methanol and chloroform, okay? And then in the presence and absence, of a lipid. And so they purposely chose a lipid because, as I already had mentioned to you, the parasites use the lipids that are coming from the red blood cells, and apparently catalyzes the formation of the hemozoid. So this is a representation of this. By having a lipid group, so in this case, this lipid that's abbreviated DOPE, you can see that actually speeds up the conversion of the monomer into its polymeric form. And without that, you have a slow rate of conversion and you have very little conversions, a circle around thing, but very little conversion, much less than 10%. So it's a big difference what the lipid is actually facilitating. All right, so here we're getting just a visual of what chloroquine is doing. So chloroquine, as you see to the left, that's a single X-ray structure, just to give us a depiction of the chloroquine with the corresponding phosphates. Because remember, it's facilitated as a diphosphate group. And so it's not as easy to see, but what we're seeing to the right is what the chloroquine can do structurally in order to impede the transformation of the heme into the hemozoid. So again, it's not as clear to see here, but we have the heme group and we have the chloroquine. And I'm just going to zoom in on a few different features. So one of the things that we can denote is that from the heme perspective, we see the iron, and that iron can get blocked by the presence of the amine groups from the chloroquine. So that can serve as a sort of coordination to the actual iron. That coordination will prevent the carboxylates from the nearby heme group from being able to coordinate. So that's one layer of what the chloroquine is doing. Another thing that the chloroquine is doing is that it's actually interacting in an electrostatic fashion, or at least in sort of a salt fashion, with the carboxylates over here. So you can see those interactions, and also to some extent hydrogen bonding, that also serves as a way of breaking up potential interactions between heme molecules with one another. And so that's what essentially the chloroquine is doing. So this is just a more of a zoomed in perspective, the same depiction of what's leading to the coordination to the iron center and what's leading to the interaction that's more electrostatic. So it's this part of the molecules I have kind of inverted, that's over here, where you're getting those salt interactions, hydrogen bonding interactions. And then you have the N1 group here that's serving as a coordination site to the iron center. So these are the ways in which that particular molecule can prevent the heme from aggregating, forming the structure, making that heme now, now still redox active, and that can then kill the parasites. All right, so going back to the structure, that's basically what's being depicted in this visual. That the I'm gonna have to compete with this. That the chloroquine is basically breaking up the possible formation of the hemozoid. Okay. Last year, was it last year or last semester, there was a person who talked about a number of chloroquine molecules in the chemistry graduate seminar. I'm not sure if you guys heard this, this was basically the premise of what these molecules can do in terms of their antiparasitic properties. All right, so as we've seen in this course, metals can play a nice important role here. And so what we're looking at is chloroquine type structures or quinoline structures and the coupling of metals. So you have ferroquine. So ferroquine has that chloroquine type structure, except that some of it has been a little bit modified, but you still have the essence of it. And that's essentially it's conjugated to the ferrozine structure. So you're trying to exploit that. Over here, we have these ruthenium-based compounds where you have coordination to these quinoline moieties. And over here, you have the gold version of it. Now you're looking at the gold one. We know that gold one tends to form these coordination number 2 structures. So you have the quinoline component coordinated to the gold through the nitrogen, but then you have the triphenylphosphine that's serving the rest of that coordination site. And as I mentioned before, aranophen, that always pops up every so often in terms of studies, because that's a drug that people commonly still explore in terms of its potential therapeutic applications that go beyond rheumatoid arthritis, or again, that goes beyond even cancer. So let's talk a little bit about some of these. You can kind of think of them as next generation drugs that have been explored. So ferroquine, and again, that's taking the quinoline moiety, combining with the ferrozine moiety. So this was first synthesized by Brocard and co-workers in 1997. It has a long half-life, which for the purposes of administration, could suggest in this study, so the 2018 study, that it might be something you could dose in a single dose of therapy in a combinatorial therapy. So I didn't really give the context of what was it being combined with, but the key thing is that because of its longevity in the body, you can potentially just have to dose it once in the context of how they were administering. And it was observed to be active against the chloroquine resistant strains of that particular parasite, the P. falciparum, which is the source of malaria, and more potent than chloroquine in other strains. So it was a very promising synergism that was observed, just much more potent compound relative to the parent drug. So again, structurally, this is a combination of chloroquine with ferrozine. And so it's believed that due to its greater lipophilicity at pH 7.4. So lipophilicity is basically a measure of the potential of that particular compound to partition between the aqueous environment or more of the lipid environment. So the higher the lipophilicity within reason would suggest that you would have greater permeability. So a compound like this, based on its mass and size, is something that could potentially be cell permeable, and it is observed to be more lipophilic than the parent compound, and this defined at a pH of 7.4. So propose that because of that lipophilicity, it may have a greater accumulation within the digestive vacuole than chloroquine itself. But another important thing is that it can facilitate interactions with exposed carboxylic groups. So to an extent, we already saw how that was occurring with chloroquine itself, but you also have the iron that's present within the ferrozine that can also potentially facilitate this. And it can generate hydroxyl radicals through Fenton type chemistry. So an important feature of ferrozine is that it is redox active. So you're now bringing in something that's going to facilitate that. Plus, you're trying to basically break up heme from becoming this, this polymeric structure. So now you're trying to augment the amount of redox active species within the digestive vacuole. So here, what we're looking at is some of the belief of the chemistry that's facilitating this. So here, we're looking at the formation of the hydroxyl radical. So in this context, what we're looking at is how you get this disproportionation into hydrogen peroxide into oxygen, and then how that hydrogen peroxide then can react with iron. So that could be iron that's just labile iron that's present within cells. Okay, so that will lead to the transformation from the iron into the iron 3 form, but then you get the formation of this hydroxyl radical. And so there's where you can start triggering some Fenton chemistry. And then you also have the ferroquinone itself interacting with hydrogen peroxide, and you lead to the formation of the hydroxyl radical. So you can see how this can augment this particular type of chemistry, the Fenton chemistry, a pretty classical chemistry, but that can lead to this unregulated generation of hydroxyl radicals. So ferroquine entered into phase 2B clinical trials. So this was in a combinatorial fashion. So a co-treatment between this compound and artemisinin. And so this was performed in different patients, various parts of Africa. But in this study, so this is 2021, it appears that it was not efficacious. And the reason why it was believed not to be very effective is because it induced vomiting in patients. So basically not enough is getting, I guess, internalized or metabolized and getting absorbed into the body. So yeah, because of that excessive vomiting, not very potent. So here we're looking at another version of a metallated compound exploiting that quinoline component. So this is the dinuclear ruthenium compound of chloroquine. And so here we're looking at something that is as a study observed to be more potent than the parent compound against different CQ resistant strains and other strains that are not CQ resistant. So here, when we're just focusing on the actual ruthenium itself, that is ruthenium 2+, that's low spin D6. So that's going to be something that's diamagnetic. As depicted here, the coordination is coordination number 4. But it's believed that that may not necessarily be the physiologically relevant coordination, that you might have some amount of bridging between these groups, and you can potentially have bridging like this that could possibly increase the coordination number. However, that's significant, who knows? But basically, that's what's been proposed in terms of the relevant chemistry of this particular group. All right. Let's look at the gold version of this. So here we have gold 1 and the associated coordination structure. So Navarro and co-workers synthesized a series of linear 2-coordinate gold-1 and also, although not depicted here, square planar 4-coordinate gold-3 complexes. That is probably all the way back, more reflective of what I showed you over here. Sorry. It's a little harder when I'm on my. See if I get out of this. Probably more reflective of what I had shown you over here with these 4-coordinate structures for gold-3. All right, let's go back. All right, so it turns out that this particular compound, as depicted here, was the most promising that they observed in their study. So these are just a few of the references to if you're interested in looking at this. It was observed to or measured to be more lipophilic than the parent compound and more efficient at blocking the formation of the beta hemeton, which is part of the process of the formation of the hemazoid. All right, so I just want to give you that perspective of just what ways that people have explored metallating known compounds for, in this case, an antiparasitic purpose. All right. So what I want to move to next, and parasites obviously fall in line with this, but here we're looking at the superbug dilemma. So are you guys familiar with the superbug dilemma? Okay. So basically, this is a very, very real situation that we're dealing with, which is that a number of microbes have evolved to a form that they're really resistant to many of the antibiotics that exist, right? Partly because of just the nature of how quickly they evolve, but partly because of human misuse of antibiotics. So we have the superbug dilemma. And so I'm going to give just a perspective of, of bacteria. So we have an orientation of compounds that exist and how they were created in terms of being able to treat bacteria, but then where we are in terms of the development of compounds or what we have available, what tools do we have available to fight bacteria, pathogenic bacteria. So it's just a cartoon representation of what defines a gram-negative and what defines a gram-positive bacteria. There are some bacteria that are a little harder to distinguish between this really, black-white distinction between bacteria. There's some that are sort of on the borderline. But this is our typical perspective bacteria, where the gram-negative, they're distinguished by having this outer membrane, okay? Then you have what is the periplasmic space, and then you have a cytoplasmic membrane. So you don't have all those layers in the gram-positive. So that's a big structural difference in terms of the surrounding of the actual bacteria. So the typical way of being able to distinguish them is using what is known as gram stain. So I thought it was pretty cool that this 2015 paper kind of explains that there was a bit of a misconception of the staining. Nonetheless, the actual way of evaluating the staining is correct, just that what's the origin of that is not necessarily correct. So what I'm showing you here are just the textbook representation of antibiotics that have been developed, and they're broken down into classes. And so what I'm showing you here is where originally, when people were developing antibiotic compounds or assessing them, the idea was that these compounds, and it's broken down into classes, what type of bacteria they can affect, what are some of important examples of them, is that these compounds target a specific feature in bacteria that are not present in humans. So in that way, they will be selected for bacteria. So just look at a few different examples here, where we're looking at this mechanism of action, which is targeting this inhibition of protein synthesis that is a molecular machinery that's present in bacteria, or inhibiting the cell wall synthesis. That's something that would not be relevant to our cells. You also have inhibition of DNA synthesis, but targeting specific enzymes that would not be able to affect us. Another type of protein inhibition or inhibition of folate synthesis, something that we're not capable of doing, although we do exploit folate, but not, we don't actually synthesize it. And so this is a perspective of compounds and, to an extent, why they were effective because of their selectivity in terms of their mechanism of action. So here's just another representation of this. Again, this is just textbook representation. So this is from a medical school book, where you can see certain types of compounds, and these are represented slightly different in terms of their naming. You have like the classical beta-lactams, the vancomycin, bacitracin. You probably have heard some of this, or been treated with some of these penicillin. And so these will be something that can break the cell wall, it can affect the synthesis of it. You have those that can target nucleic acid synthesis and then features that are related to that, like for instance, inhibiting folate synthesis. You have those that will be able to target protein synthesis, and so those groups that are present. So that is the perspective of known antibiotic agents, and basically what people have done over time is that when things become resistant, what you try to do is make derivatives that can overcome some of that resistance. But even that now has become something that's quite limited in terms of its application. So we're here right now, we're in this antibiotic resistance. So this is probably getting a little bit old, but it's still very relevant. This quote, stop referring to a coming post-antibiotic era, it's already here. So this was from the CDC director, Robert Redfield. So due to the rapid mutation of pathogenic microorganisms, superbugs have evolved, which are antibiotic resistant. So in 2019, the CDC reported that these superbugs can cause more than 2.8 million infections and 35,000 deaths annually in the United States. And that's just the United States. The report lists 18 antibiotic resistant bacteria and fungi in 3 categories. You have urgent, serious, and concerning. Antibiotic resistant germs can share their resistance genes. That's what makes them scary. They can share their resistant genes with other germs and make them untreatable. So it's a type of crowdsourcing that occurs. So there is a tremendous need for the development of new strategies to try to tackle this problem. So where is the field in terms of antibiotic development? So to an extent, I already mentioned that there's making derivatives of known compounds to try to overcome some of this resistance, but even that has hit roadblocks. So you have other efforts that are being made. Part of this is driven by where some of the bias in the field. So I began the course telling you that there's a big bias against metals, right? And so that leads into even in the antibiotic field, where antibacterial compounds that are now being explored are no longer fall into the category of things that are drug-like. So this in a medicinal chemistry course, I'm not sure if any of you have taken medicinal chemistry here, you will learn about what will be properties of small molecules that would lend themselves to be something drug-like and potentially orally available. So there are certain features about their mass, their lipophilicity, and other features like that that's going to be important. So it turns out that some promising antibacterial compounds don't really fall in line with some of this bias. So by not conforming to the physical, chemical, and reactive functionality guidelines developed to direct the discovery of new orally available therapies. Many potential new antibiotics have been excluded from synthetic libraries because of not falling in line with what would be considered drug-like due to these drug design axioms in mind. So this is I personally thought this was a very important study. This was in 2020, where Vaskovich and the team, they ordered and screened over 295,000 compounds from the community for open antimicrobial drug discovery. So the COADD, I think this is based in Australia. And so this is a place that they will screen compounds. If you want to send your compounds, they will screen them to try to test their drug, well, not necessarily drug-like, but their antibiotic potential, but also their just general toxicity. So from this study, a significant amount followed this drug-likeness. So falls in line with what you would expect to be a drug. So demonstrating that the drug design axis has permeated even into the academic research efforts, and that makes sense, right? Because you want to fund a lab, so you're going to fund a lab based on where the trend is and where is industry actually trying to develop drugs. But it was also observed that some of these compounds that were screened actually fall outside of the conventions, and a considerable number, 906, so 906 out of almost 300,000 of metal-containing compounds were found amongst the submitted compounds. So the COADD, they offer free service test compounds, and I've taken advantage of them to be able to test some compounds. A little bit slow, but still, it's nice to be able to do this, and it's for free. So what they do is they start off with a 1-dose concentration. So they dose at a 32 micrograms of compound per milliliter volume of solution. And so they test against, in their first phase, against these microbes, 4 gram-negative bacteria. So these are the gram-negative bacteria that they are testing against. You have E. coli, you have the multi-resistant, I'm not going to butcher this, MDR, and you have those others. You have the Pseudomonas aeruginosus, so really classically studied gram-negative bacteria. You also have these gram-positive bacteria, a really standout one that it's a very pathogenic agent. This methicillin-resistant Staphylococcus aureus, also referred to as MRSA, and that's a source of infection in hospitals. So it's something that you really need to watch out for. And also these fungi, so Candida albicans and so forth, that they test. So this is like their first screen. They do a 1-dose concentration and they see, does any of these actually stand out in terms of their activity? All right. So as I mentioned, so there is generally a disregard for metals in terms of their potential antibiotics because of this belief that metals are toxic, right? So you have a common denominator of lead drugs, lead structures of the pharmaceutical industry across the globe, most almost exclusively organic in nature. So although metal-based antimicrobial compounds have shown effectiveness, the inorganic chemistry space is still largely ignored due to that miscorrelation to toxicity effect. So, in this study, they are proposing that metal coordination chemistry can lend itself to a lot of chemistry that has yet to be fully exploited because of the 3-dimensional structure that they can offer. So they offer this new novel chemical space that could lend themselves to, breaking some of the limitations in the antibiotic drug discovery. So going to the findings of this paper, again, 300,000 compounds screened, roughly 300,000, of which 900 were actually metal containing. Of those 900, you had these metal elements that were actually were some of the ones that were actually in these compounds. So the ones that are highlighted in yellow are the ones that were actually being tested. So what was observed in this study? So here you see an array of the submitted compounds, and then you see them categorized into the following. So you have the categorization of active and non-toxic. All right, so what does that actually mean? So they define active as showing a activity against a microbe. It doesn't have to be all of them, just one of them at least, within the dose range that they test. But then active and non-toxic means that it's active against at least one microbe, but non-toxic against a mammalian cell, or in this case, human cell, 2 of them they tested, that they show very low cytotoxicity against this. So you obviously want active and non-toxic. That's the direction you would want to go. So it turns out that the more abundant first row deep block elements represents almost 50% of all these compounds. Ruthenium being the highest number of submissions of the metal-containing compounds that were actually screened. And so you see here the significant antibacterial activity of metal-based compounds. And so you see how many pertain to which elements. So here we're getting the number of active compounds and how many contain these particular metals. So the numbers that are there. And then you have from this active and non-toxic, obviously that's going to drop. And so you're going to see which ones contain wood metals, and the ones that stands out the most would be platinum in terms of the ones that are active and non-toxic. All right, so it turns out that you have a far better hit rate for active metal-based compounds, 27%, in comparison to the overall hit rate for the COADD, which is only 1.6%. So of the metal compounds that were actually screened, 27% were observed to be active. So that's active, not necessarily active and non-toxic. So that was actually a very interesting finding to do. See, let me get out of here because it froze for a moment. All right, so is a metal-based compound hit rate affected by toxicity effects? All right, so I kind of spoiled it, but that's fine because how did they really assess toxicity? So the way they did it was by screening against 2 types of cell lines. One, which is the HEC-293, which is a human embryonic kidney cells. And then they also tested against the human red blood cells. So what they were measuring with these numbers, CC50, which is basically like IC50, and then HC50, which is like IC50, but in this context, they're looking at the ability of the compounds to lyse, to burst the cell. So that's what's called hemolysis. And so they were measuring the concentration of the dose of the compounds that's going to trigger that. So that's how they were able to assess toxicity. So removing all hits that display toxicity left a total of 88 metal-containing compounds. Now that takes a hit rate of 9.9% for non-cytotoxic hits, still substantially enhanced compared to the 0.87% for the overall library. So even when you remove those that are toxic, you still had a higher hit rate, active and non-toxic for metal-containing compounds of that bunch than the overall, of the active compounds that were not metal-containing. So the data to the right is basically showing you the filtering of the compounds that are active, the compounds that are non-toxic, but then those that are actually active and non-toxic. All right, so this is not a study where they're trying to understand mechanism, they're just proposing mechanism. So they don't do the mechanistic studies. So they've reasoned that some of these are inert metal complexes where you have intact compound binding to a specific bacterial target. So the actual compound itself is what's serving as a potential active species. But then you also have those that they believe to, and this is all based on aqueous speciation, right, of these compounds. Those they're believed to be owed to some amount of labelling. So partially labile metal compounds. So you're going to have some ligand association must occur for the metal species to bind a bacterial target or itself be toxic. And then those where labelity is key, where you're going to have a release ligand, which the ligand is possibly the source of toxicity. And that's important because then the metal is playing the role of a transport agent, not an actual, toxic agent in this case. Or the release metal is the source of toxicity and the ligand is playing the role of an ionophore. Okay. So why I say that I contribute to this, I didn't contribute to that study, no. After I read that, I was like, well, I have a number of titanium compounds. I would like to screen them. And so I won't say we've got anything major, but I wanted to just screen a number of them. And more importantly for us is to make sure that what we're seeing, if we see anything, is due to the possibly the presence of a metal in those compounds, not just the ligand, because that's something that's could be the case. So a number of metal-containing compounds and the ligands, free ligands we sent. And so these are some of the results here. Nothing stand out. So as in like we didn't like wipe out any of all of them. The few of them where we saw the activity and non-toxicity, we had a couple of them. So we had one against MRSA, and then we had one against the C. albicans. So we were just trying to rationalize this one right here because this is the compound that we have studied for anti-cancer purposes. So this is what we have studied in our lab is this idea of a transmetallation in terms of an anti-cancer application. So that's something that could be true even on the bacterial level, because some of the things that we propose has to do with this idea of being able to exploit the labile metal pool, in this case, the labile iron pool that many bacteria will thrive from iron. And so we believe that's a possibility, and how that can impact the particular enzyme that's in bacteria that's present in humans, but it's a different version of it. And so still a relevant chemistry that we think that it might be the source of why we were seeing some of this activity. Obviously, we didn't explore this further than just looking at the screen and proposing what we thought would to be the result here. All right. So for the last part of this, what I'm going to talk about is this idea of exploring the roles of metals that have known antibiotic properties and looking at how they may be able to enhance the antibacterial properties of known antibiotics, right? So for instance, silver has been long known to be antibiotic. In fact, silver was once used as an antiseptic for newborn babies to minimize the risk of getting neonatal ophthalmia, which is a type of conjunctivitis, can come from gonorrhea or chlamydia from the birth mothers. In the 1880s, a German doctor began the practice of putting silver nitrate in babies' eyes as a preventative measure. This is a practice that's no longer actually applied. So silver is used on surfaces in hospitals to reduce nosocomial antibiotic-resistant diseases applied in water cleaning systems. There's currently an initiative, so you see some amount of the academic world that's exploring the use of silver in synergism with antibiotics to see if that combination can potentially be useful against the multi-drug resistant bacteria. So here is an example or of a table that comes from studies here. So what we're looking at here is not as easy to see, but you see a number of common antibiotics from different classes, the beta-lactams, the quinolones, the aminoglycosides, the spectinomycin, and then you're getting that's being co-treated with silver one, and then the organisms to which they were applied. And so the effects were across the board was that there was a pronounced increase in terms of the potency of these compounds, which was believed to be owed to a synergism between the silver and these particular compounds. So if you read closely some of these effects, you can see that the relative amounts have increased. Some of them are more moderate, meaning not so pronounced, and some of them are actually pretty pronounced. So it does appear that silver can work in synergism with different classes of antibiotics and expand their spectrum effect. You will see that there are people that are even trying to design metal complexes with silver using antibiotics as a coordinating feature of silver. So what is a proposed synergistic mechanism? So this is just proposed, not necessarily has been actually studied. So this is a 2018 paper where they try to make sense of how can the silver be contributing to this. So here we have an example of a type of antibiotic, which is this aminoglycoside. So the idea is that the silver has this capacity to enhance the antibiotic cellular uptake of that type of antibiotic by essentially destabilizing the membrane. So destabilize the membrane, that antibiotic now can actually enter into the bacteria, and it could have its known effects. But also it's believed that the silver, once it enters within the bacteria, has a capacity of altering intrinsic membrane proteins, may target ribosomes, which will produce misfolded proteins that are directed to the inner membrane of gram-negative bacteria, also altering permeability. So ways in which the silver can facilitate this property of basically destabilizing the membrane and allowing for a greater uptake of the actual antibiotic. So from this perspective, not necessarily something to do with the coordination chemistry, but simply how the silver might allow for this type of compound to be active. And then you also have this proposal of how silver might lead to ROS generation, but it's not something that's actually commonly accepted. So there has been some observation of silver leading to ROS generation, but silver itself is not a redox active metal. But it's believed that by its interaction with certain key biomolecular pathways, it could lead to this formation. For instance, it could lead to perturbations of the electron transfer chain. It could possibly destabilize metalloproteins, like for instance, the iron sulfur cluster proteins that we briefly discussed earlier. It could lead to even decreased anti-ROS activity. And so that could possibly, offset the regulation of ROS. But nonetheless, this is what's believed to be a possible additional feature of what the silver can facilitate in terms of chemistry. Okay. So any questions about this?
En el último slide, no puede hacerlo directamente, pero sí lo puede hacer indirectamente.
Indirectly, possibly. Yeah, possibly because it is a soft metal, and so maybe because of that softness, you might be able to disrupt some of these pathways. Y a su vez eso es lo que realmente generaba la producción de los y no directamente. Right, that would make sense. So I sent you guys, just to finish up, I sent you guys Oscar ready to go. I sent you guys a copy of last year's article that we're going to submit this week, but I sent it to you because it's very relevant to what we're discussing. In that article, we looked at copper and how copper can potentially facilitate contributions to this, to be able to try to target the superbug problems. But yeah, just wanted to send it to you guys before I actually finish it up. All right, any questions before we head out? Any doubts? All right, everyone, so enjoy your break and I'll see you next week.
Sí, bueno, si online.